Hi everyone, welcome to another episode of my machine learning journey. Today is August 31st, 2019. I would like to talk a little bit about the paper review sessions that we in our machine learning group were doing on yesterday, the Friday. So let's see what are the things that we covered in our paper review. So we were reading this paper called Semantic Autoencoder Zero-Shot Learning. So this is what the paper is about. It was a paper that were published on the conference CVPR 2017. I know this CVPR is pretty high profile machine learning conferences. So I guess there are also other high profile conferences such as ACL. It's probably for NLP. I haven't gone to any of these conferences, but I always hear a lot of news or a lot of advancements from these conferences. So this paper is about semantic autoencoder for zero-shot learning. Why did this paper catch my attention? It was mostly because of the semantic keyword. Because when we were doing, say, natural language processing project, when we are doing all those embedding work, we always try to find an embedding which can map the meanings of the sentences or words into a vector space. So that's why I started to read about this paper. And then in actually for this paper, I think more than one person actually implemented this paper. So this is one of the implementation that were using MATLAB. So you can see that all of these file extension are .m. So it's implemented using MATLAB. And then there's also another guy who also implemented the paper using PyTorch. I think it's being linked here as well. So let's see this GitHub repo. So this one I started already. So this one, and you can take a look at how it's doing for this paper. This paper is mostly on image. So how to actually embed images into a semantic space. So we were discussing in our paper review sessions yesterday, mainly covering 3 points. So the first point that we were going through was, of course, the simple autoencoder. And then for the second point, then we evolved into semantic autoencoder. And then we were also discussing, so what is the difference between semantic autoencoder and simple autoencoder, and also in this paper, how it's achieving the purpose that semantic autoencoder, which can bring new things over simple autoencoder. And then lastly, we were also covering the concept of zero-shot learning. Personally, I think zero-shot learning, the idea is very similar to transfer learning. I don't know if it's just a new word for transfer learning. If anyone knows about it, feel free to comment below. And then also we were also raising a few questions. So one is what is the difference between generative model and discriminative model, because I think it was brought up when we were discussing autoencoders. We know that simple autoencoders are not generative model, but variational autoencoders are generative model. And then so I brought up the question that then can generative model do classification or not? Because we know that discriminative model can do classification. And then so someone also mentioned that she thinks that naive Bayes model, which should be generative model, but people still, like almost everybody still use naive Bayes model to do classification. So I think it's a good, knowledge point to do some research on. So I'm just maybe gonna talk a little bit more details what we were discussing for 3 of these points. Simple autoencoder, I think it's pretty straightforward. So it's just that when you have the input layers for your neural network, and then you set up a bottleneck middle hidden layer, which is doing dimension reduction, has much less units than your input layer. So therefore, artificially set up a bottleneck for to encode the input data so it can learn the representations of your input layers. And then you decode it. So, and then for your output layer, you are trying to reconstruct the original input data through the bottleneck. So through backpropagation and optimization process, that the neural network can learn the representation or embeddings of the input data as much as possible that can serve the maximum reconstruction accuracy. So that's how the hidden embedding for the input data are learned for both images as well as texts. And then so a lot of people claim that for simple autoencoder, it's not really necessarily learning the semantics of your input data. And then actually I wonder like why? And then so then what is the difference of semantic autoencoder that can actually learn the semantics now? Like what is the magic about it? So I think from this paper, what it's saying is, so when you, like in the just the regular autoencoder, when you set up the like the middle layer, hidden embedding layers, it's just that the neural network is just through backpropagation that it's just naturally automatically learning the embedding space. So you're just projecting your input data into that embedding space through the optimization process and finding the linear transformation, or maybe not, it's not really linear transformation, because if you so if you actually add quite a few activation function and so on, then it probably already became a nonlinear transformation. So that's how you can learn how you can actually non-linearly projecting your input data into the embedding space. So what this paper is providing is that so it actually defines a semantic space other than the embedding space that the regular autoencoders construct. So in this paper, such as in which page? In page 1, 2, 3, 4. So in the section 3.3, so you can see that that's how it's defining the cost function or the objective function that it's trying to do to find this semantic space. So from what we were discussing in the paper review sessions yesterday, someone mentioned that it's doing through like humanly artificially designing embedding dimension. So for say if you are projecting animal pictures, then you just define, okay, so I want my first dimension to measure the black and white stripe. And let's say like I want my second dimension to measure the size of the ear or size of the eyes and so on, because when you are just doing regular autoencoders, that dimension is not humanly defined, but through just automatically learning from the input data itself. But now in this paper, it says that you actually artificially constructing a semantic space and defining all these different dimensions mean for your hidden layer embedding space. And then it's setting up an objective function. So through optimization, you want to be able to bring the embedding space as much as close as possible to the semantic space. So the semantic space is like a hyperparameter that a human provides. And so therefore, still through backpropagation, so therefore, by learning through data, then you want to bring your embedding space as close as possible to the semantic space, so it can learn the embeddings, the semantic embeddings. And then I actually brought up a question in the discussion. So then how do you initialize that artificially submitted, like provided semantic space? Like for say, so which is like you are providing a ground truth. Like say, if like, for my zebra picture, then my first dimension that measures black and white stripe, it will be 1 or like maximum value for that dimension for a zebra picture and so on. So this then becomes in the sense of supervised, right? So because from what I understood before, supervised learning, it's always in classification, like you are providing a class or a label for your data. But here, it's actually providing a supervised embedding matrix. So you're providing a matrix which describes the ground truth of each of the semantic dimension of your input data. And then through the autoencoder process, then you are using objective function and optimization process that you are bringing the embedding space as close as possible to the semantic space that you're providing, that supervised in semantic matrix. So which is, I find, it's something, interesting. So you're not really providing a supervised label at the output layer, but you're actually providing a supervised layer for the embedding layer, which is, quite interesting to know. And then, so I guess this is the main difference between semantic autoencoder that this paper describes with simple autoencoder. So, and another one that this paper talks about is zero-shot learning. So, for my understanding, zero-shot learning is very close to um, transfer learning. So they're both trying to solve the problem that you need to do the problem of a test data that you actually haven't seen in the training data. So I know how transfer learning is doing this is that you usually have a large model that were trained in a really huge data set. So therefore, you have already learned all the optimized weights for each of the layers. And now you have a much smaller data set on hand, which probably did not exist in the training data. And then you want to be able to do like classification task for these new data that you have. And usually, so why transfer learning is suitable for is that um, it usually can solve the cases that you don't have a complete label for all of your data. So maybe you just have like a few. You only have a few labels. You only have labels for some of your data. So therefore, you can use those data to then fine tune the pre-trained model in transfer learning to learn to fine tune the weights, and then therefore you can still be able to input the data that you don't have labels for, and but still are able to do classification for those data that you don't have labels for. And so what this paper describing looks to me is delivering similar idea. So either you're doing a problem of domain shift using transfer knowledge from what you have learned before. So what this paper does is, through constructing this embedding space that you have constructed a projection function. So therefore, even for like, so you will learn the semantic space, and then you will learn all the parameters, the weights to be able to project your data into the semantic space. And therefore, for the new data that you have not seen in your training data, through feeding your new data into the network, you are still able to project them into the semantic space, and then finding their measurements in those corresponding semantic dimensions that we were talking about. Um, it's so, well, I guess this is probably like a general idea for this paper, but I think it would be still interesting just to, see the implementation, the co-implementation that I was showing earlier. So, and then also play with some of the, toy data and to see how it's actually playing out, right? So yeah, this is what happened in the machine learning journey for my past week. I'm looking forward to sharing more of the newer learnings with you. If you like it, feel free to click a like and subscribe, and then look forward to my newer update. Thanks for listening. See you next time. Bye.